食べを全部開けて、開けますよ。Yeah, Hololive official mentions the 1 week left to get the application in. Yeah. Yeah, we'll see. Yeah, well, whatever the case, 1 week or not, crap. Okay, where's my Apple Pencil? Let's get started. Yeah, we got 1 week to build a portfolio. That's not that doesn't sound very good. It's okay. We're gonna target, I guess we're gonna use that as a short-term goal to kind of, what is this? Let's see. Yeah, so we're gonna use that as a short-term goal to kind of get our shit together and, well, again, we'll hope for the best. Oops, let's close all these YouTube tabs that we don't really need, or rather, can't really use. Right, and then we're gonna get back to work. Here's the question. Yeah. Okay. Okay, so we'll try to connect the screen. Although I realized for Quantum I can actually probably stream it without worrying about blurring anything, because the professor actually provides the, what do you call it? The professor actually provides the recordings for the lecture on YouTube, or published publicly. So I assume that means it's okay to show the information, or maybe it's not become an issue yet. So I probably should get permission for that. Okay, so will this connect? Come on, I need a no, please. Oh, the window's open. This accessory is not. I think I really need to get a new Thunderbolt to Ethernet, or Lightning to Ethernet adapter, or maybe I just need to upgrade to an iPad that uses USB-C. Okay. Yeah, 1 week until the Hololive EN round 2 auditions, but more importantly, 3 hours and 50 minutes to submit this assignment. Yeah. Come on, connect, please. Let's try this. Let's reboot it. Yeah. I mean, I think all it realistically proves is that I probably don't have the time to juggle all these things at once. So yeah, so we're gonna, whoa, that's not as big as I was planning to make that window. Okay. Yeah. Means I need to optimize something to make it doable. Anyway, okay, so, right, so we found an equation for Cm dot. Integrate this from 0 to t using the condition of the 0th order. Actually, wait, no. Excuse me. All right, so you get Cm dot, and consider a system that starts out in the state psi capital N. So at t equals 0, psi capital N. Okay. The 0th order coefficients are, they say C capital N of t is equal to delta N capital N. Well, oh, okay, I see. So, okay, so if a state starts in capital or some psi n, some state psi. I want to call it psi naught, but I guess that's confusing in terms of nomenclature. I'm gonna drink. Okay. So we have some state psi that it starts out in. Okay. Or this is the starting state. So that implies that then the Cn coefficient, or coefficients, I guess. Yeah, I don't know about this notation, but I think C lowercase n of t should then be delta n capital N. That is to say, the coefficient for when n equals the state that that we just arbitrarily set, the coefficient will be 1. And for any other state, it should be 0, just using the Kronecker delta definition. And then by that logic, since capital N and state lowercase m aren't the same, then the Cmth coefficient should likewise then be 0. So what do we do with that information? Oh, Skullmeat, welcome back. Yeah, how are you doing? Okay, so note that the value of the exponential is 1, since en minus en equals 0. Yeah. Integrate this equation from 0 to t using the condition of the 0th order. Okay, so for the Cnth coefficient, we get this integral. For every other one, we get this equation. Oh, we get this equation, which you'd then integrate to get the coefficient at m. Shork? Sorry, what does shork mean? I'm gonna Google it right now real quick, but what is this thing? Monster Legends. Shork is a nature attacker that can deal great amounts of damage. What? Shork play Super Metroid. Oh, is it Gura? Is that what I was missing? Is she playing something right now? Oh, it is Super Metroid. Okay, I see. Okay. Yeah. Sorry, I gotta focus on actually finishing this though, or finishing as much of this as possible. So, well, I'll try to tune in, but we'll see how far I can get with this. Oh, short shark. Okay. Excuse me. Yeah. Okay. So. We're gonna use site A because I don't want to copy variables, and it also kind of forced me to understand the content. Okay, so if we implies that then C A of t equals, or yeah, the Cn of t's should then be the Kronecker delta n and a, and further implies that since I guess also assuming state A is not M, then that would imply that the mth state is 0. Oh, disconnected again. Yeah, I don't get what the screen mirroring wants me to do. I don't know why it's so temperamental about connecting. I suppose it's because it cheaped out on buying an adapter. Anyway, okay. Okay, so Find the first order perturbation we substitute into the result of part A in equation 4. So we get Cn, so in my case Ca, part A. And Cn dot equals, okay, so I think for every other coefficient. Let's move that down. We'll say then that yeah, okay, so we'll assume that then using that we get Ca dot of t is then equal to 1 over IH bar, the sum, and then Cn we're gonna swap for drag delta Na, e to the I t over h bar em minus en, or I guess e, so m is swapped for a, so this is a inner product. Or m is a, yeah, okay. Or they can't see anything. Okay. Okay, there we go. So that will be our equation for the derivative of the 8th term. Again, then we'll evaluate the inside of the sum, or the excuse me, the sum. We get 1 over IH bar. This Kronecker delta only has a non-zero value for n equals a, so then we get e to the ITH bar EA minus EA, which is then just equal to 1, and then psi A H bar, or H prime, psi. What's up my throat today? Psi A, this is just going to then be the expectation value of H prime. So we get, I guess they expressed it as negative I over H bar, and then psi A H prime, psi A, C A T, okay. So then I guess we want to get rid of that derivative, so we'll integrate it with respect to t once. We get negative I over H bar, and roll from 0 to, where do you get 1 minus here? Why do you get 1 minus? Oh, yeah, Little Noise, welcome back. How are you doing? Let's see. We get 1 minus, note the value of the exponential is 1. Where does that 1 minus come from? One term, integrate, or to evaluate the integral for, so H prime n d prime. so we 1 minus condition 0th order. I think the coefficient. Well, I suppose it makes sense that the coefficient would be 1 minus that quantity because we want to know the, I guess the coefficient squared should give the probability of having that state at that time t. So 1 minus certainly makes sense. At the same time, I feel like not having the 1 minus would also certainly give the probability. Where does that 1 minus come from? Sorry, what is this? I'm making a station I call the Great Core. Cool. What kind of station? Inserts 2 in your writing. Well, yeah, I think yeah, if I got a magic 2, that would certainly be a little bit awkward. It would complicate the normalization of the state. Not significantly, but you know, yeah. Anyway. So where does this 1 minus come from? Explained here? I don't think so. Okay. Let's see. En minus En equals 0. I know you get 1 from that, but so that's why the exponential term goes to 0. But why do you, when you integrate negative IH bar H prime N N, you should end up with, what is that? Okay, so I suppose the question is how it goes inside the bracket. Why is there a 1 here? What am I missing? That goes to 1. You put the Kronecker delta in for Cn. I don't think we swap in H prime for anything. Well, let's leave it the way I think it is. I think every once in a while there's a typo in these things. It could very well be the case right now where it's just a typo. Okay, so you get that for some state, or whatever the state you started in. For the other ones, this should be Cm equals 0, so condition of the 0th order. Yeah, I'm pretty sure it's supposed to be a typo. I don't know what it could be. Alright, so then, alright, so C, yeah. So we'll just say for other coefficients. Cm dot equals -ih bar h. This entire thing. And then we integrate it Oh, there is no sum because we're just looking at that specific coefficient. So if we just take the integral, wait, what? How are we? Because it's like that. I'm confused now. Let's go a couple steps back. So we got Cm dot. This is the sum of C, or this is Cm dot, some equation. And it's some constant times the sum from, or I guess overall possible states of some constant times the perturbation times some exponential. Okay. And then we suppose that we start at some state psi. So from that we can determine that at least at state, or at least at time equals 0 before anything's changed, C sub A, the coefficient for state A, should have a probability of 1, and then everything else should have a probability of 0. So that's what we're saying here with the delta. Show us where the coefficients are. Okay, so that, yeah, okay, so that's what the delta here is, I guess to say. C capital N is Kronecker delta, lowercase n, uppercase n. C capital N is that, yeah. And then Cm dot, you would evaluate for H prime N capital N. Why is it H prime N capital M? Yeah, no, it feels a little obtuse the way they're proving it, but I think, let me see. So Cn, right? So we established Cn. So at the very beginning, the probability, the increase in the probability to get any other state, in like the instantaneous change, should be dependent only on Cn. Yeah. So then that's why every state Cm, or Cm being some arbitrary other state, is the inner product of state, whatever state you're checking, the initial state, and then the perturbation to figure out how much the perturbation actually influences things. So this explains that. The question is, why do you need to specify the equation for the nth state? Okay, and that's probably why it's 1 minus, because I guess what you're really evaluating is, what you're checking is essentially, what is the change in probability if you're evaluating the coefficient? What is the change in probability from the initial state to some arbitrary time after? So the reason it's 1 minus is because we know that the state C sub n, or the way I defined it, C sub a, started out with a probability of 1, or 100%. And it's changing from that. It must change by decreasing. So therefore, if we evaluate Cn dot, then that should be taking away from the initial probability, which is 1. So that must be why that's 1 minus. I don't know why we bother establishing that, but okay, so let's do that. Let's write that down. Okay. So we're going to keep psi sub a though. So we understand that okay, so we understand that some, I'm a little confused, so we're just going to copy the notation as well. But we're just going to make sure to borrow some my favorite math problem is 2 to 64. That's not really a problem, is it? It's just a number. Although 2 to 64th, let's see. What is the max number that can be? I don't know, but it's 8 bytes, right? So, however, I don't know if there's an 8-byte long data type, but it's however many values that can hold. I guess a double tends to be 4 bytes. So, well, no, I think some languages will store it as wait, did I say 8 bytes? Yeah, 8 times 8. Yeah. Yeah. It should be 8 bytes then. So I'm sure it's some number. So you'd have to just look. So I guess I could just look for. I guess I could just throw it in a calculator. But it's also, I was gonna say it's also the max value for an unsigned integer in whatever languages store integers as 8 bytes. I don't know what that is, but it'll be that number. Okay, so anyway, I'm gonna drink again. Yeah, I don't know, my throat's so dry recently. Okay, so coefficient value Cn, so we're gonna say that C capital N dot is gonna be 1 over IH bar sum Cn t, this is over index n, e to the it over h bar, e sub, I guess, n minus e sub lowercase n, inner product psi sub n h prime psi sub lowercase n. Right. So then from there, we should be able to also know that, let's see, what else can we say about it? Yeah, so all these C sub n should equal 0 except for C sub n, which will equal 1 at time t. So I guess I should say in that case. In that case, not only do we have the case C sub lower or uppercase n dot equals this equation, but we also know that the coefficients will, or there's only one term in this sum that has a non-zero coefficient, which will be 1. We have e to the it over h bar, e sub n minus e sub n, uppercase n, because, that's the only one with that index. And you have psi sub uppercase n, h prime, psi sub uppercase n, because that's what we stopped at. This is going to be 1. So then we know that c sub n, uppercase n dot, is equal to, I guess, negative I over h bar times the inner product and this h prime being evaluated. Yeah. Of course, we'll take the integral with respect to t in that case of this, and we get negative I h bar over this quantity. Uppercase n. All right, dt. Of course, let's see, the change in c uppercase n, or wait, no, I should say cn starts out at 1, so c sub n starts out at 1, so if it changes, it must decrease. So cn at time t is probably more like 1 minus this integral IH bar over integral psi sub n h prime psi sub n uppercase for all those dt. Okay. Okay, so that's how we would get IH bar and then that integral. Okay. Let's see. For every other coefficient, we already established that c sub m dot, the entire thing dotted, is equal to IH bar, or negative IH bar, integral, or no, sum from, well, actually, wait. Yeah, so c sub, well, let's write that thing. So for, yeah, so every integral, well, we know that c sub m dot is going to abide by this sum. Obviously, if we're checking every freaking integral, then that means we're going to not have the sum, we're going to have the individual terms there. So this will be c sub m dot equals negative I h bar over h bar c sub m of t. Well, we shouldn't have c sub m because we know the coefficient is going to be 0, so we probably don't want to multiply it by that. Oh, looks like something disconnected. Yeah, something's wrong with my throat today. Oh. Text 12 just mean doubling made it to 34th power. 34th power, what would that be? I have no idea. Okay, so let's see. Yeah, so it would be this, but I guess evaluating, let's see, but the only state contributing is c sub capital N. So we don't have every nth state, we only have the ith state, or sorry, not the ith, we have the capital nth state contributing some probability, and then e to the it over h bar e sub m minus e sub capital N. That's what it should, yeah, okay, there we go, that's what I was missing. Okay, and then psi sub m h prime psi sub capital N. Okay, so yeah, okay, so then this is going to be 1, at t equals 0, as we established earlier. So then c sub m dot equals negative I over h bar, e to the it over h bar, e sub m minus e sub capital N times this inner product. Take the time integral, some mth derivative will then be this integral. Okay, the probability of transition from state n to state m is given by, okay. What even was the question that we got? I really should be doing vocal exercises from now on. Yeah. Okay, so let's see. Okay, so transition probability. Assume that h prime is constant, then we can, okay, h prime is constant, the perturbation is constant. Okay, and now that's just a simple integral then. Is that a negative IH bar? That's a positive IH bar, I guess. Yeah, I guess it's a positive IH bar, so it doesn't cancel perfectly, but Okay, so we get this number then. And I guess we have to square that? Yeah, gross. Okay. Factor out the 2, the e to what? 2. Oh, well, they squared, okay. So let's see. EM minus EN with H prime MN in the negative somewhere. And then they convert. So make it 1 minus. Note that we factor out EIEM minus ENT over 2H bar in the second line. We use representation with sine function terms in the complex exponential. It's gotta talk. Oh. No look like that. Let's see. Okay, so apparently, if you factor this out, then it's convenient. If you factor this out, you factor out a 1/2. You end up with e to the, what is it? I guess you're, what? Oh, disconnected again. Okay, so let me see. So we'll wait for that to reconnect. Oh, that was fast. Okay. So we factor out an I over 2h bar and then all that crap. So you should end up with an e to the. I guess we should end up with e to the I over 2h bar em minus en t minus e to the negative I over 2h bar em minus en t. Let's see, is that right? Let's see. Let me think. So you're factoring out an I over 2h bar em minus ent. So let's just call that like b or something, that entire thing b. So you factor out b over 2. That would be the same as let's see. You have e over b. You factor out an b over 2. Let's see, if you were to multiply them, it'd have to be over 2, b over 2. So logically, then you should end up with the b over 2 left in here. And if you factor that out, then to get 1 here in the first place, you'd have to have e to the 0, which means that this other thing earlier must have been negative b over 2. Yeah, okay, yeah. Yeah, so you should end up with a bunch of e to the whatever over 2's. Yeah. Okay. So then, let's see, sine, yeah, so I guess sine exponential form. I feel like there's a 2i that you needed to, yeah, there's a 2i. If you'd e to the, yeah, so where's the 2i? Oh, there is a 2i that was factored out, okay. So then, you end up with and this is just going to be sine of, and then all of this turns into x. Everything except the I becomes x. So it's going to be em minus en t over 2h bar times all that stuff then. Okay, and then we gotta square it. So then p equals cm squared, which equals squared. We have a positive 4. Okay, why does that keep disconnecting? Seriously. Do h bar. Okay. I really might just buy a new adapter. How much does an official adapter cost? Let's see. Apple Lightning to Ethernet adapter. How much is $30? But I paid like $15 for this anyway, so. Oh wait, this is Thunderbolt, not Lightning. USB Ethernet adapter. Come on, where is that official Apple Lightning to Ethernet adapter? Yeah, Belkin, right. Belkin offers a super expensive, like $90 one. Does Apple not offer one? Okay, you know, I'll worry about that later. You know, I guess I could try that powered switch. Whatever. Alright, so this is going to be our probability to transition from state n to m. Okay. Now, okay, so that's what we wanted at the beginning. Find the probability that our result, excuse me, is E2. Okay, so we want to go from V0 is significantly less than E1. So V0 significantly less than E1. So we are trying to find the transition from probability 1 to 2. When does the potential come in then? feel like we never used information about the potential. Or say V naught is significantly less than E1. V naught is significantly less than E1. You find P1, you find H prime 1, 2, we need the unperturbed wave functions. And oh, right. We need V naught as part of finding how the perturbation affects the okay, now we are. Oh, top left. Welcome back. It's been a while. How have you been? Oh, I realized the screen's black. Let's see. You still haven't set up donations. Well, I mean, I think I might have to make a record. Actually, so I get asked that a lot. So, or maybe not recently, but every once in a while someone asks about it. So I think I should probably record a video about my stance on that, so I could just link people to it. But yeah, not for the foreseeable future. Yeah. You know, keep your money, invest it, you know, buy a cookie, get some coffee. I don't know. It's probably better that way. Yeah. Anyway, like, yeah, how you doing? I'm just, you know, doing quantum mechanics and shit as ever. All right. So anyway, so we want P12. Okay. So we want, okay. So we're going from, we want to know the probability. Okay. Let's see. So we want the probability to go from E1 to E2. Did we ever say that, or say that we were in the ground state? Actually, when did we ever say we were in the ground state? Because E1 implies we're in the ground state. Oh no, it literally first line. A particle of mass m is initially in the ground state of the one-dimensional infinite square well. Yeah, so right. Yeah, all right. So then we want P from 1 to 2. So that implies that then by our notation, n should be the ground state. N equals 1, m equals 2. So then we want that probability, which is going to be C2 squared, which is going to be this massive equation that I got right here. There we go. Except, okay, so n is 1, n is 1, 1, 1, 1, and m is 2. There we go. Actually, what about that t? We have a t dependence that never ought. Oh, no, t comes in because we need to know how much time it takes, and I guess we're assuming it's a trivial amount of time, or yeah. Anyway. Right. So then let's just, okay, so let's solve this part. Psi 2, or bra psi 2, h prime, ket psi 1. Psi 1 and psi 2 respectively are going to be, actually, since for the infinite square well, psi sub some state n, psi sub n is going to be square root 2 over a sine of n pi x over a. That's what we solved last semester. So psi 1 x is going to be rad 2 over a, lowercase a, sine of pi x over a, psi 2 of x is going to be square root 2 over a sine 2 pi x over a. And then what was h prime? H prime. How do we know it's V naught? Yeah, okay, so then this becomes then the integral, let's see, h. Okay, so that thing equals then this integral from 0 to, I guess from negative infinity and infinity of square root 2 over a sine of pi x over a h prime square root 2 over a sine of 2 pi x over a dx。残らないんだったら寄付も何も心配しなくていいのにぶっちゃけ。So we can say that's 2 over a from 0 to a over 2 sine pi x over a v naught sine 2 pi x over a dx. Let's see. Okay. So then we have to solve this integral. We're going to do 2v naught over a integral 0 to a over 2 sine pi x over a times, and this is sine 2 times pi x over a, so we use double angle, our favorite little equation. We get 2 sine pi x over a cosine pi x over a dx. Okay, so then, right, u equals pi x over a, du equals pi over a dx, so that implies 4 v naught over a times a over pi, integral 0 to a over 2, sine squared pi x over, or sine squared u times cosine u du. Crap, what was this? Oh, wait, no, that's even simpler than I was thinking. I was gonna use like the sine squared cosine thing, but I can just set sine as my, or no, I could just set cosine as, or sine as sine pi over ax as the function as u, and then that'll be cosine pi over ax times the inside derivative inside, that's just pi over a, is going to be du then. Pi a dx, I believe. Wait. dy pi over a, let me think. So u equal to sine pi over ax. Take the derivative of both sides. We get du equals cosine pi over ax times the derivative of the inside, which is going to be pi over a dx. Oh, and they have an a over pi. Okay, so divide the or bring the reciprocal over, you get a over pi du equals cosine pi over ax dx. Okay. So then you can bring this thing and make it into 4v naught over a, integral 0 to a over 2. It'll be u squared times a over pi du. Yeah. So you end up with 4 v naught over pi, integral 0 to a over 2, u squared du, so we're going to get the 1/3, u cubed, 0 to a over 2, so we end up with 1/3 a cubed over 8. We have 4 v naught over pi here, got the 0 over there, that'll be 1/2, so we get v naught a cubed over 6 pi. Oh wait, I messed up my integration bounds, didn't I? Because that doesn't sound right. Let's see. Where do I change it? Oh, the screen mirror broke again. Never mind. Okay, so a cubed, there we go. So integral bounds. Yeah. Here, so this is what I was supposed to do. Here we go. So let's get rid of the integral bounds there. 1/3 u cubed, so we're going to have 4 over 3 v naught over pi times u, which was sine cubed of pi over ax, evaluated from 0 to a over 2. There we go. So sine cubed of pi over a over 2 minus sine cubed 0. This pi over 2 times is just 1, 0. Yeah. So we end up with 4 v naught over 3 pi as our probability. Or wait, no. Wait, no, that's going to be the inside of the thing. It's not the probability. So P equals then this top part all just becomes 4v naught over 3 pi, and then e sub n equals n squared pi squared h bar squared over 2ma squared, so we have e1 equals just pi squared h bar squared over 2ma squared. E2 equals 4 pi squared h bar squared over 2ma squared, so then E2 minus E1 equals, well then 3 pi squared h bar squared over 2ma squared. So then we'll plug that in. 4v naught over 3 pi times, I guess, 2ma squared over 3 pi squared h bar squared, quantity squared, sine squared. This is on the top, so we have 1 over t over, let's go to top, t over 2h bar, 3 pi squared h bar squared over 2ma squared. There. Okay. So we end up with 9. Now let's do this first. So you have 8 v naught ma squared over 9 pi cubed h bar squared, quantity squared. Then we have sine of 1 h bar cancels. So we have 3 pi squared t over 4 ma squared, I think. Oh, I forgot the h bar. H bar t. 4 ma squared, okay. So it's going to be 64, 81, v naught squared, m squared a to the 4th over pi. Oh, maybe I wasn't supposed to multiply that. Let's see. Which term gets multiplied? Which term gets multiplied? It said quantity squared there, but maybe that was what I was supposed to do. 2ma squared over... Oh, did that entire quantity not get... Oh, it does, yeah. Prime squared. Yeah, so that should get squared, I think. Yeah, I think that does get squared. It turns into a big number, but pretty sure that does get squared. So you end up with 64 v naught squared m squared a to the 4th over 81 pi to the 6th h bar to the 4th sine of 3 pi squared h bar t over 4 ma squared times 4. Okay, so whatever. What is 64 times 4? $256. And that should be our probability. Doesn't look right, but whatever. It's close enough, I assume. All right, next problem. Okay, so harmonic oscillator, so harmonic oscillator of mass m, charge E, and classical frequency omega is in its ground state. Uniform electric field is turned on at t equals 0 and is then turned off at t equals tau, used for certain time-dependent perturbation theory to estimate the probability the system is excited to its nth state. So we're going from, let's see, so we have a harmonic oscillator, mass m, charge E, frequency omega. Okay. perturbed, okay, so perturbed at t equals 0, off at t equals tau. Probability that we go from ground state to nth state. So that is going to be, let's see, if we follow the same work as we did before, then is that the same? Harmonic oscillator, right? So what's the equation for it? Let's see. Okay, what was the equation for the harmonic oscillator states? Can't remember. H bar I E n minus, okay. H bar over 2m omega. H bar over 2m omega. It's showing up inverted. Why is that? Which one was it? Let's not worry about that. Where is it? So we want to do the same thing essentially that I did before. Let's see, we want the probability that we go into this state. So Along x-axis, direction of oscillation, which fields apply, then perturbed Hamiltonian is HE x bar the field. Transition. It's called, okay. Okay, so they define the x hat direction as, or the x hat operator, I guess. Okay, yeah. So I guess right, so let's see. H for the harmonic oscillator, we have H prime is equal to this Hamiltonian squared x hat squared. I think it's the sum of the, no, I guess to multiply them, yeah, to get the right values. Oh, and screen mirror broke again, didn't it? Okay, so 1 over 2 h bar p squared 2m Okay, so what else do I need? So yeah, so this is A construction, A annihilation, so 2 h bar times creation annihilation is equal to m omega x hat squared plus rho hat over 2m squared, I guess. Yeah. Oh yeah, that's not perfect, is it? 1/2 plus that? Okay, and the screen mirror is temperamental as ever. Okay, so creation annihilation gives us pretty much the similar form, except we're off by, let's see, over 2m, 1/2 m omega squared x squared. So let's have an omega squared x squared left. M omega h bar. Added 1/2 to this, h bar over 2h bar, that doesn't do anything. 2m omega h bar, right? Oh, h bar omega is out here, so eventually you want h bar omega 1/2 plus creation annihilation. Okay. So if we hit it with h bar omega, or I guess we do plus 1/2. So let's keep those divided by each other. Okay, 1/2 plus a plus minus plus 1/2 plus over 2h bar m omega x hat squared plus 1 over 2h bar. Okay. And then what am I missing? Did I multiply these in the right order? Actually, wait, these won't commute, will they? So yeah, these won't commute, so I have to redo that. 1 over 2 m omega h bar. Okay, so we get m squared omega squared x squared plus m omega x hat, or minus m omega x hat ip hat plus ip hat m omega x hat minus I squared p hat squared plus p hat squared. This will be minus m omega I x hat p hat plus m omega I x hat p hat m omega squared, or m squared omega squared. Let's see, so this can be m omega I x hat p hat minus, this should be, this is the wrong order, p hat x hat. Let's see, so I guess this is, what is the, let's see, let's see, commutation relation. Let's see, so x hat p hat commutator, which is I guess it's xp minus px, so negative this xp minus px, which is in ih bar. So then we should end up with positive m omega h bar, m squared omega squared x hat squared plus p hat squared 1 over 2 m omega h bar. So then we get m omega x hat squared over, well, I guess 1 over 2 h bar. We'll only bring in the m and omega plus h bar plus p hat squared. So we want to bring in a h bar to cancel that guy out. So I'm going to bring in h bar in. Do we have to subtract it then? So why did they add it here? Is there supposed to be a negative on this guy? Negative. Started out as a negative. I should have made it a positive, which had turned it into a negative. Yeah, okay. Okay. No. Wait. Okay. So m omega x hat times negative I p hat, that's the negative, I p hat times m omega x hat, so I p hat m omega x hat. You move that over, you get the plus here. No, wait. Okay, one more step. Slow down. One more step. It's going to be m omega I negative x hat p hat plus p hat x hat. Okay, we bring out a negative m omega I. We get x hat p hat minus p hat x hat. Okay, this is the canonical commutation relation. We get I bar or IH bar out of that. Negative m omega I So then we should end up with I squared there, so m omega h bar. Yeah. 1 over 2. Or, yeah. Okay, so then positive m omega, or m squared omega squared x hat squared plus p hat squared 1 over 2 m omega h bar. How do they get 1/2? Positive 1/2. How the hell do they do that? Or h naught is supposed to be that. Kind of need to take away an h bar from that, don't I? Okay. Well, let's pull out... Okay. Let's see. So yeah, what if we do plus 1/2? We do plus 1/2. So then we get 1 over 2 m omega h bar m squared omega squared x hat squared plus m omega h bar plus p hat times 2 plus, and then 1/2 but converted to m omega h bar. So we're going to need to multiply top and bottom by m omega h bar. And then we should be able to bring that in. Yeah. Okay, so we get 1 over 2 m omega h hat m squared omega squared x hat squared plus 2 m omega h hat, oh, plus p hat squared. Oh, okay. Oh, I was being stupid, yeah. All right, so then we get that cancellation. So we get 1 over, bring in that, so we get m omega x hat over 2 h bar plus 1 plus p hat squared over 2 m omega h bar 1/2 a plus a minus. Wait a sec. How am I supposed to get that cancellation? Wait a sec. Okay, let's go through it then. So last step would be h bar omega on that guy. So then we get h bars cancel. We get 1/2 m omega squared x hat squared. We do get that. H bar omega, that seems kind of unnecessary, plus h bar omega, so we get p hat over 2, or p hat squared over 2m. Yeah, so so we have that extra, so that should have been a negative. So why didn't we get the right signs? Let's see, the creation operator is defined as 1 over square root 2m omega h bar times quantity m omega x hat plus I p hat, yeah, okay. Annihilation operator is defined as 1 over square root 2m omega h bar times quantity m omega x hat minus I p hat. If we combine, or if we multiply the two, and be careful about ordering, we should get, well, combine the square roots, we get 1 over 2 m omega h bar, and then inside the quadratic, we should get m squared omega, I guess it's not quadratic anymore, or I guess it is, yeah. We get, right, m squared omega squared x hat squared, and then minus m omega x hat I p hat, yeah, plus I p hat m omega x hat minus I squared p hat squared. Next line is negative m omega I x hat p hat plus, or sorry, m squared omega squared x hat squared minus m omega I x hat p hat plus m omega I p hat x hat plus p hat squared. Factor out negative m omega I from the interior 2, you get negative m omega I times x hat p hat minus p hat x hat satisfied, or which is the canonical commutation relation. You get negative m omega I hat h bar. Or am I wrong? Is that not the commutation relation? I might have it backwards. Where is it? It might be px, in which case I totally botched it. No, it says AB minus BA, so x hat p hat should be x hat p hat minus p hat x hat. Do I just fake it and I say fudge the numbers, or? Okay, it's definitely h hat, or Hamiltonian's h omega a plus a minus plus 1/2. Where did I mess up? Hamiltonian minus 1/2. Wait, no, that is right. Oh, so therefore the Hamiltonian plus 1/2 is okay. Wait, I'm missing something. So, Hamiltonian minus, yeah, okay, wait, so this is right. So let's just double check this, do sanity check here. We do a minus 1/2 here. We get this negative. We get these canceling. I guess hit both sides with h bar omega. We get h bar. Well, let's do it like this then. Let's see. It's 1/2 h bar. 1/2 h bar. 2 h bar, there we go. M omega x hat squared plus p hat over m omega So if we hit it with 2 over omega. Wait a sec, what? Yeah, it. No, just separate the freaking terms. Okay. One half m squared omega squared x hat squared over m omega h bar plus p hat squared over 2 m omega h bar. These cancel, so you have 1 half m omega over h bar x hat squared plus 1 over omega h bar p hat squared over 2m. Let's see, what do I need? I need omega here, so let's see. 1 over h bar, 1 half m omega x hat. Okay, there we go. Okay, so a plus a minus 1 half equals that. Let's see, so if you do, well, so 1 over omega h hat, we get h hat omega times 1 over h bar 1 half m omega x hat squared plus 1 over omega h bar p hat over 2m squared. Alright, so we do the inside, we get 1 half m omega squared x hat squared plus p hat over 2m squared. 1 over omega h bar, so then we get 1 over omega h bar Hamiltonian equals a plus a minus minus 1 half. So then, let's see, a plus a minus equals 1 over omega h bar. Well, actually, wait, isn't that it? Okay, let's got it though. Let's see. My equation using equation 1 and 2. We get x hat equals You know, why did I even bother with all that? Really? Pretty sure I could have just cited all this. Okay, so Hamiltonian perturbed. Let's see, so H prime P is going to be transition probability is going to be... Do they just give us that somewhere? The way to derive it. Oh, A7, yeah. Yeah, go ahead, have a good evening. Yeah, happy Friday, I guess. Yeah, see you later. Ways to meet. Let's see. So this is gonna be NE. Okay, where's... Oh, it's 2 lines, okay. Yeah. 0 to tau. Uh, hmm. Hmm? これはどっから来る？ So that is the Hamiltonian of the unperturbed system. Oh, how they compute that? Minus 1, because I guess you evaluate the integral. Okay. An H naught N. When did we end up with an H naught N in here? Oh, okay, they're in the thing. Right, they're operators in there, yeah, so I can't just rip them out, yeah. Okay, so from the next line, N, okay, so we have N, E, yeah. Then you pull things out, you end up with that, so. Okay. E to the N. Okay, so if you evaluate this, the H naught, then we're effectively saying, let's go back a line. E to the I E N T over H bar N A minus plus A plus E minus I E naught T over H bar naught. Then we move those out, but into the T integral, 0 to tau, E to the IT over H bar E N minus E naught, I guess, yeah. N A minus plus A plus 0 dt. Let's do all of this. Okay. Okay. N1, so N annihilation plus creation, saying is times that. You're saying there's no time dependence on it anymore. N plus 1. How do I know I can't go to the N minus 1 state? Or actually, wait, no. Lowering operator on N should. Yeah, you should end up with the square root N and. Okay, so raising operator on the 0, that'll give state 1 with, I think, N plus 1 outside. What is all this crap? So this is the constant. This is all the constant. There's a negative in there that must have gotten generated from. What step was that generated in? Oh, they're using I over H bar, so that's where the negative comes from. So that doesn't matter. They have N or brought N ket 1, and this entire... How did this happen? Okay, so there should be multiple terms, but shouldn't there be more than that? Okay, well, let's try it. So, well, actually, I guess I don't need to. It's going to be n a or annihilation 0 plus n creation 0. So on the right, oh, okay, and then you argue that applying the annihilation operator to the ground state will zero this term out. But if you apply the creation operator to the 0th state, then you should get n1. Of course, if you applied the annihilation to the nth state, then that wouldn't really help you. But okay, so this is how you justify integral 0 to tau. Okay, because you could take it both directions. Yeah. So it over h bar en. Okay. All right. n1 dt. I guess we can. It's just gonna be a 1 over 0, so that shouldn't have any time dependence. It shouldn't. The orthogonality of the nth and the first state shouldn't be dependent on time. Is it? Maybe, but I don't think it is in this case. So I think we can factor that out. So right. So now we have e to the I over h bar en minus e naught times t dt. Or sorry, the integral from 0 to tau of that. So I do the integral. We get 1 over I over h bar en minus e naught e to the I over h bar en minus e naught t value from 0 to tau. We get e to the I over h bar en minus e naught tau minus 1 times the annoying big coefficient. I'm going to call it IH. No, let's just leave it I, because it's not negative IH bar. That would have just been, or negative I over H bar would have just been IH bar, but I don't want to deal with the negative, so we'll leave it like that. Then you have that IH bar E square root H bar over 2m omega, all inside of a square. They have this S sub n1. Oh, okay, so that's where this thing. So the bracket's going to be a Dirac delta n and 1, or not Dirac, Kronecker delta n and 1. So e squared. Oh, Konosuba, welcome back from, or eggs in general. Heard that and instantly got reminded of the cancer that is broadcast. It's cancer, but unfortunately, it's the kind of, it's like, I don't know, I think there's like a type of cancer that you can use to actually attack cancer cells, right? It's like that. It's your enemy, but once you get to use it, it's actually helpful. So you kind of have to live with the cancer. Or maybe it's not a cancer cell. I can't remember. It might have been a modified bacteria that you can use to target cancer or something. I can't remember what it was, but it's like that. Okay, so Kronecker delta, n and 1, this crap. So you should have like h bar squared or something, don't you? Where is it? Huh? Where does the h bar go? Huh? They canceled it with something. Oh, no, it's still, it's in the new, no, the numerator one I already have. Where'd the one in the denominator go? Oh, they did cancel it, but they didn't cancel the i's for whatever reason. Oh no, I guess they did in a later step. Okay, so we'll do that. We'll convert that to Kronecker delta. I still don't get why it's not h bar squared, because it's in the denominator of the denominators, so it should be in the numerator then. Oh, but the h bar is supposed to be in the denominator here. Oh, because they have, no? Wait, what? Was this supposed to be negative I h bar? Where? Let's go back. Oh, this was 1 over IH bar that I had in the very beginning. That's why something was weird. Yeah, 1 over IH bar. 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 There we go. There we go. There we go. Oh, LSAO, welcome back. Here for 10 minutes. All right, yeah, sounds good. Yeah, yeah. I guess good work this week. I think you said you had school, right? So, let's see. Yeah, so this should be negative IH bar over here. So negative En minus E naught. So you should end up with a negative then, trailing at the very end. Yeah, you do. Okay, okay, okay. So this is right. Okay. Tau minus 1. Cancel those. You end up with a negative E electric, or negative charge E electric field E square root H bar over 2m omega Kronecker delta n sub n and 1 over 1 minus E n minus E naught, which we'll fill out in a moment, times E I over H bar E n minus E naught tau minus 1. Okay. Yeah, school may be wrong tomorrow. Oh, that's good. That's good. I guess it's the weekend, right? So you can relax a little. That's good. That's good. Okay, so they have a lingering, oh no, that's not a lingering eye. Okay. So, yeah, we'll leave the Kronecker delta in there, but it's this entire thing squared. Okay. So, yeah, okay, so let's do it then. So we have E squared, or charge E squared, electric field E squared, H bar over 2m omega, 1 over E n minus E naught, quantity squared, times E I over H bar, E n minus E naught, tau minus 1 in parentheses, and then I guess when n equals 1. And, or the probability for that when n equals 1. But n is the state we're jumping to. Wait a sec. Wait. We're jumping. We want the probability to go to state n. But this probability is only non-zero when we're going from state n to state 1 to state 1. What? Doesn't make any sense. Oh, and this quantity should be squared. Wait, what? That doesn't... Wait, let me check the question. A harmonic... Okay. Use the time-dependent perturbation theory to estimate the probability the system is excited to its nth state. Yeah, the first state is the ground state. What am I missing? Wait, what? I'm pretty sure this is Kronecker delta because you're resolving the... You're evaluating for the orthogonal... Wait, harmonic oscillator states. Are those orthogonal? Oh, they must be orthogonal, right? They must be orthogonal to each other, right? Wait, are the states of the harmonic oscillator orthogonal to each other? Well, wait, they have to be, or else I can't write it as Kronecker delta. And they do. Here. Okay, you know what? Leave it as a Kronecker delta. That's what the math says, so I'll just leave it. Alright, so then for these guys, let's do En for H, the harmonic oscillator, is N plus 1/2 H bar omega, so En minus E0 equals, or actually wait, so, right, so En is that, E0 is 1/2 H bar omega, so En minus E0 is equal to N H bar omega. Yeah. So then we can put that all in. I guess that quantity squared, so we have N squared H bar squared omega squared. E to the I over H bar quantity N H bar omega tau minus 1 Kronecker delta N1. Okay, so they'll leave it at that. Yeah, you know, we can simplify it one line more. I think they want us to simplify it even further, but I'm not going to. H bar over 2 M N squared H bar cubed omega squared times E to the I N omega tau minus 1 times Kronecker delta N1. Okay. Calling that our probability. Yeah. Frickin' bracket notation, right? Okay. Alright, next one. What was the question? Ohanian 19. Suppose you have an electron in one-dimensional harmonic oscillator potential. Okay, so V equals 1/2 M omega naught squared X squared. 1D harmonic oscillator. Some field. Okay. Okay, so, okay. Electric field. How do you, what the hell is this symbol? Looks like a phone, like the old phone receivers. Okay. And delta phi equals E. So phi equals thus minus that. What's the point of defining phi? Oh, is that simple phi? Symbol's not phi. Let's see. In the x direction, right? Harmonic oscillators H prime T equals H prime cosine omega T t, probably time t. That doesn't really clarify much for me. They all define some phi. So whatever the squiggly thing is E is the field, some function that has the same label as the field evaluated at 0, cosine omega t in the x hat direction. They use that as justification to define the Hamiltonian as the unperturbed Hamiltonian minus the perturbation. Okay, so whatever. I think we would call this H prime. So then the total Hamiltonian will be H naught plus H prime, or I guess minus H prime. And that'll be for the harmonic oscillator. That's going to be e squared of 2m plus 1/2 m omega squared x squared, x hat squared rather, minus whatever the symbol is, evaluated at 0, cosine omega t. And I guess there's some directionality to it. Yeah, let's keep the x hat in there. Sorry, what was it? What are you studying? Oh yeah, it's more quantum. More quantum. Yeah. Oh wait. Oh, that's why. It's because x hat could be the position, or sorry, x hat could be the position operator or the direction x. I guess those are. No, because one's an operator, one is well, I guess the axis is kind of the operators, and you know, whatever. Anyway, harmonic perturbation H prime is equal what? What is this H prime cosine omega t? Man. I need time to study. I need time to work on the freaking application. I need time. Let's see. Okay, no, let's skip to a different question real quick. What else can we do? Here's a simple one. It says justify. Okay, so justify the following version of the energy time uncertainty principle due to Landau. I don't know. Delta E. Okay, so justify delta E delta T greater than or equal to h bar over 2. Where delta T is the time to execute a transition involving an interchange delta E. Under the influence of a constant perturbation. Explain more precisely what delta E and delta T mean in this context. Delta T is the time for T to reach a peak in its oscillation. So note delta T is the time it takes for P of T to reach a peak in its oscillation. Oh, interesting. So delta T is the time it takes for P of T to reach a peak in its oscillation. So energy time uncertainty principle. Anything? Well, okay, so the one thing I know from that is then delta T is reach a peak in its oscillation. P of t is the probability for the particle well, P for some energy. Oh wait, sorry. So justify the following version of that energy time uncertainty principle. Oh, Vaders, welcome back. Yeah, I'm not really gonna get affiliate anytime soon, so and I believe channel points is an affiliate option. I can explain, but sorry, right now I'm a little bit on a time crunch. I guess you could wait until midnight when I have to submit it, and then I can explain. Or I'll make a YouTube video about kind of my thinking regarding getting affiliate, or rather not getting affiliate at some point. So if you can wait for that video, or 12 o'clock, whichever is more convenient for you, yeah, that would be, yeah, sorry, I'm on a little bit of time crunch. So right, so delta t is the time it takes to execute a transition involving an energy change delta E. Okay, so right, so the energy change delta E, from what we can get from there is that from delta E, or rather the energy change, we have a definite energy, right? That's the whole benefit of having the Hamiltonian, the energy operator, basically being the same. So you're at state, if you're at some energy, and you then you change some energy delta E. So you go from energy like A to energy B. And delta T is the time it takes to do that jump. So state A and state B, those are both states of definite energy, which is why the explanation here that delta T is the time it takes for P of T to reach a peak in its oscillation makes sense, because P of T is the probability of finding a particle in a certain state. So delta T is the time it takes for that probability value to max out at 1. So how do you justify then that delta E delta T should be greater than or equal to h bar over 2? Okay, well, first of all, let's do stuff. Okay, so delta E is the change in energy from one state to another. So that implies we go from a state of definite energy A to another state of definite energy. Yeah, sorry, sorry, I saw your comment right now. Energy B. Yeah, sorry. Again, if you can wait until midnight, so another hour and a half or so, or you can wait till I upload that video. Sorry, I get asked that a couple times, so I've been meaning to make a video or something so I don't have to, well, first, so I can explain slowly without rushing, and B, also, so, yeah, sorry, I usually explain, but I'm a little bit on a time crunch. Okay, so definite energy B. Okay, so, delta E is the change in energy there. Delta T is the time it takes for that change to occur. I'm going to need a hint. Let's see. So Heisenberg and uncertainty principle of energy and time, which is given the transition takes some time, energy is available only for the time dt, so it can be considered as the time width of energy pulse. The bandwidth contained by the energy is given by, I guess, oh, so you're supposed to associate it with wavelength? Time it takes to execute an energy pulse. Is it talking about wavelength then? Or sorry, well, wavelength, right? That's the actual, yeah, I think. Let's see how other people explain it. There's only one guy that explains it. Yeah. I don't. Okay. Well, what happens to the particle? let's think of it like that. So you're going to do an energy transit, or let's just assume some arbitrary energy transition occurs. Your particles like vibrating or whatever shit at one, it's like oscillating at, let's say, delta t is the time it takes for p to reach a peak in its oscillation. Delta t. So p of t is the like each state other than the current, well actually every state has some p of t associated with it, and those will kind of oscillate, or often it ends up being an oscillating function. So delta t is the time for that to, like, for one of those states to have its p of t oscillate to like to its max, like to 1. And then that's when the transition delta E occurs. So how does that have to do, what does that do with the energy time uncertainty principle? How do we relate that to h bar? Or maybe we don't need to relate it to h bar over 2 specifically, especially since we're supposed to just take a wordy kind of justification for it. Maybe it's just we want to, so it's going to be some constant which just happens to be h bar over 2. Okay, so how about we think of it like that? Let's just think of it like this. Let's try thinking more like delta. Let's try just thinking of it as like delta E delta t is greater than or equal to some constant c. Let's think of it like that. Okay, so then what can you glean from this information? Let's do that. Delta E delta t greater than or equal to c. So energy and time, some constant, energy and time. Let me think. So what can we associate with energy that would... Oh, interesting. They use h bar and what is this, frequency? Let's try to... I want them to be inversely proportional. We just want to be able to prove that there's an inverse proportionality between time and energy, I guess. So, you know, they well, first of all, yeah, so when like one goes up, the other goes down. Or wait, although I guess they're not directly proportional, because then it would be exactly equal to some constant. Heisenberg uncertainty principle in time which combine variables, given time transition takes place, and given the transition takes place in time, the energy available is, well, energy is only available for time dt. Energy is only available for time dt. Width of the energy pulse. I don't... Let's see. Well, you know what? This is... Let's see if Slater has a better explanation. We want the first there's a Korean third edition on Slater. That's interesting. I mean, I guess there's no reason why there shouldn't be one, but just thought it's funny. So this is, it's chapter 9, number 18. Maybe they have a better explanation, because I don't get how you're supposed to go from... I guess you're supposed to use delta E and say and kind of break it down such that you get some sort of cancellation with delta t. Or, yeah, I don't know. Alright, so C explanation. Will Slater give me any extra views? No. Okay. If there's spontaneous absorption, then it will involve taking energy from the ground state to the ground state of the electromagnetic field, but we can't do that because the ground state already has the lowest allowed. Is this number 19? This is number 18. Previous one. Previous one's a different question. Although, actually, wait, no, we were assigned this question. Interesting. So, 9... Okay, I'm not going to bother about it, but basically the question in Chapter 9 got moved to Chapter 11. Yeah. This page is empty, really. Further solution. Okay. Alright, so that didn't really help. Constant... under the influence of constant perturbation. Delta... Explain more precisely what delta... Okay, so delta t, delta E, delta t, so... Yeah, so... change in energy, given amount of time... Well, okay, let me think of it like this. So, if you change... Well, let's suppose you had a minuscule energy chain. Let's say you're at the ground state and you move like right above. Could that take a long time or a little time, I guess is the question. So delta E is small and delta T is going to be... Well, then that should just be a really small number then. So set minimum... Justify the following version of the demonstrated principle. It takes time to execute a transition involving an energy change under the influence of constant perturbation. Explain more precisely what delta E and delta T mean in this case. Delta... let's go to... let's see... Delta T, delta E. So yeah, if we were to try to support it, so for example, let's say delta T was super small, then delta E would have to be massive to retain the h bar over 2 relation. Let's say it was like we're talking about like nanoseconds or something. Delta E would have to be massive. So delta T is the time it takes for PUT to reach a peak in its oscillation. So that's how long it takes for the wave function to change to a higher, to one with a higher associated energy. Okay, I don't know. Yeah. Me, B, let's see, this occurs when the side B states C sub B squared equals 1 when the new state side B's. When the new state side B's coefficient CB squared equals 1, time it takes for the coefficient to change. I don't know what to say. Okay, whatever. So we're gonna keep going. We're just gonna call that done. Not solved, but like we're done with it. I need a drink. Oh, LSAO, right, heading out. All right, yeah, sounds good. Thanks for coming by. Take care, stay safe. If you do go rowing, you know, stay safe, but, you know, have fun. And, yeah, we'll see you later. Nice to meet. Okay, so let's go to this fairy one. At t equals 0, an electron is assumed to be in the n3 eigenstate, an infinite square potential well, which extends from... Okay, so we have an infinite square potential well. We have an n equals 3 state, an electron there. And it's from negative a over 2 to a over 2 in terms of width. I guess we have the 0 here. At tau, probably time, equals 0, an electric field is applied with the potential V equals EX. E equals EX. Electric field is then removed at time tau. So it is determine that the probability of the electron is in any other state at t greater than tau. Or I guess, so basically after the perturbation is removed, what is the probability the electron is in any other state? You have the perturbation. Okay, so V equals EX, B equals EX. So that means that the perturbation probably looks something like this. For x equals 0, there is no perturbation. Yeah, so I guess this is how I draw it then. Okay. We have the bottom of the well, or what used to be the bottom of the infinite square well. We have some linear function that goes like this, so it's diagonal. We have it end at negative a over 2, and then I guess the height, so we should have a over 2, a over 2, negative a over 2, 0. This should be EX, so EA over 2, EA over 2. Okay, so this is what the well looks like. We have some states. At the n equals 3 state, we have an electron. We want to know if it jumps or not, whatever, who cares. The point is, if it's with the perturbation applied at t equals 0, and then removed at t equals tau, what is the probability the electron just moves? So that should then be, okay. Okay, so then probability electron moves to any other state is just then the probability that the electron, or it should be just 1 minus the probability that the electron is in the original state. So actually I really have to go to the bathroom. Okay, yeah, right. So the probability, we just want to know what is the probability is any other state. It's any other state. So then rather than compute all the other states, which are infinite, so it would take an infinite amount of time, I guess thankfully that's what quantum computers are for. But I'm not a quantum computer, or at least I'm a biological quantum computer, but I don't know how to program that component. So yeah, anyway, so I can't do that. So we need something that can be solved in finite time. So we'll just compute the probability to stay at the state 3. Yeah. Okay. First of all, I'm going to go to the bathroom. Okay, let's get back to work. Back to work. Yeah. We're gonna put a little more effort in for at least the next couple hours, and then once we hit midnight, we're free, and then we can start Operation Meet Iago again. Yeah. All right. Okay, so the probability to stay in state 3. First of all, we're going to borrow some work. I think, let's try. Okay, where was that? We already did the infinite square well. Okay. So borrowing work from number 1, or the first question they gave us, at what point did we plug in the actual perturbation? Near. Okay, so basically, number 1 was the infinite square well as well. And I believe most of the work I did was generalized up until I plugged in the actual perturbation. Here we go. So we're going to copy this. The probability, or rather the coefficient Cm, or is everything else equal? Yeah, because we haven't plugged in the perturbation yet. So let's see. So from above, let's see. Griffith's, what was it? 11.27? 11.27. Above, we pull the probability to have moved into any state M to be this equation, I guess N to M, and we'll do, it's gonna be P3 of 3. Oh, wait a sec. This equation doesn't work for that, does it? Because you end up with 0 in the denominator here. But yeah, what do I do then? Fuck. Nandakke. Can I not do that where I just do 1 minus the probability? Or wait, maybe I think there actually was a different equation for staying in the same state. I think I solved for something like that earlier. Let's see. So here it is. Right, we solved for something different. Here we go. The probability to... Okay, no, this is if changes, it must decrease. Is the probability to be in that state? Yeah. So we, from earlier, let's see, we said the probability to be, or the coefficient for the wave function, or sorry, the coefficient for the state, for staying in the same state, or the state that you're initially in, is gonna be this integral. So the probability to be in state 3, or the coefficient for state 3, is going to be 1 minus I over h bar integral inner product psi 3 h prime psi 3 dt. Is that right? Is there? I thought there was another, like, whole bunch of other crap that goes along with it. I guess not. Okay. Let's grab the wave equation for the infinite square well, the nice and convenient one. And we're gonna copy paste that right here. Boop. And h prime is gonna be, I guess, it's not a constant, it's gonna be a function. It's gonna be ex. So then we have 1 minus I h bar integral square root 2 over a sine of 3 pi x over a. Don't we need to? No, I guess not. No. If we had the difference of the energies, then that's exactly the problem we were trying to circumvent earlier. Sine 3 pi x over a dx. 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 That doesn't make sense. It should be dt. There should be a time integral. Where did the t go? Let me think. So then h prime must have time dependence. I mean, that's the whole thing with perturbation, right? So how do I add the time dependence back to the perturbation? H prime squared t e I h. Oh, wait, no. Since the energies are the same, the exponential with the t term in it should vanish. That was the whole simplification of this step. So then it doesn't matter then? No, because the probability to move into other states should change. Oh, it's calling me, welcome back. Sorry, I'm just thinking. So the probability to shift into or to transition to a new state, that should change over time, and that kind of probability should come at the cost of being in the initial state. So so there should be a time dependence. Probably to be in the original state. Let me check the wave function. Did the wave function... Oh, wait, I guess... Do I have to... The wave function's time dependence. Do I tack that on? Do I just tack that on then, I guess? Maybe? Ends up 0 if you do that, so...
If omega equals omega naught, perturbation theory will fail at some time t. What is the critical time?
Oh, no, that's different question. No. Looking at this.
Central V equals Ex. Such a field is removed at time t. Determine the probability that the electron is in any other state at t greater than tau.
Let's see. If it's a dx integral, alternative, if I had dx dt somewhere in there, I could convert it to an dx integral and get a proper probability out of it. Probability. Wait, no. So,
wait. United state at t greater than tau. So, okay, so.
So basically our integration go from 0 to tau, then, right? I think. Go from 0 to tau because that's when the perturbation is in effect. And no, it should still be a function of t because tau is a time value. Equals a lot of time applied. Potential V. Electric field is then removed at time t. What am I missing? Infinite square well. States. Eigenstates of the infinite square well are square root 2 over a sine n pi x over a. So where did the time dependence come in again? Let's see, so e n t. Take the derivative. State. The coefficient g c n n t. Yeah, the component with t disappears. So you have to take a t derivative. But h prime is independent of t. Is only dependent on what spatial position you have. So we just pull it out of the integral then? Is this just linear? I mean, that sounds kind of crazy, but... Well, then what do we plug in for x then? We need to integrate over x at some point, right? Because we want to get the... We want to evaluate how much the perturbation influences the thing, so... Is that all it is then? You do the integral dt as an evaluation from 0 to t, or 0 to tau. And then you have the inner product of h prime with the two psi equals 3 states. That should be tau. Integral dx of square root 2 over a sine 3 pi x over a, and then ex sine of 3 pi x over a, square root 2 over a, like that. And then you'd factor out, so 1 over h bar, or 1 minus I over h. How do you get the imaginary component out of the frickin' way? Whatever. Yeah, so it'd take an imaginary amount of time. What the heck? I think w over 2 to a over 2. 2 over a x sine squared 3 pi over ax dx. Is that even a standard integral? Even function times odd function. What? Tau? Just be 0? Equals 1? Doesn't make sense, but whatever, I don't know anymore. Oh, what is it? Sorry, I saw the video link just now. I'll take a look at it after I submit this. But yeah, like x is an odd function, sine squared is... Wait, no, is sine squared even about 0? Let me think. Sine squared. I need to look at what the function actually looks like. Yeah, sine squared... Okay, Desmos, Desmos, do your thing. Sine squared x. No, not, okay, sine, fine. Sine x squared. There you go. Yeah, it is even. So then, even function times an odd function. So, about an symmetric integral. That's just going to be 0. Equals 1. I don't know. Something doesn't make sense there. Or maybe it is trivial, but I'm going to bet on that not being the case. Whatever, but we're going to leave that because I'm not really sure what to make of it. Okay, so the last thing we have to do is go back to number Ohanian 19 and figure out what the heck we're supposed to do with that harmonic oscillator. Right, so now let's restart. Let's restart. Okay, so what information do we get? We have an electron in a 1D harmonic oscillator. Okay, so electron 1D harmonic oscillator, right? So that means we have a unperturbed Hamiltonian, which is kind of just the same as the Hamiltonian we usually expect. And it's 1/2 m omega squared x squared plus p hat squared, or I guess x hat squared, over 2m. That should be our unperturbed Hamiltonian. We are given v equals 1/2 m omega naught squared x squared. we are given a perturbation, I think. It's an oscillating electric field. So we have an electric field that's this weird symbol evaluated at 0 times cosine omega t in the x hat direction. Okay, cool. So we got our information. Let's delete all of this. So what can we glean from this then? Actually, wait. So the potential. So what is the takeaway here? The Hamiltonian, they set up as this. Or they set up the total Hamiltonian as this. This is the oscillating electric field, but not the potential included. Right, okay. So yeah, so we're gonna say the total Hamiltonian is gonna be equal to the unperturbed Hamiltonian, I guess minus the perturbation. Minus the perturbation? Oscillating electric field. Harmonic oscillator. I thought you would add the perturbation to it. H prime. So is electric field not consider the perturbation then? Okay, let sanity check. Textbook time. The perturbation should just fundamentally be okay, there we go. Perturbed Hamiltonian. Get some hits for it. Come on. Perturbation theory. How about that? If you just go to the first hit, or the first relevant hit of perturbation theory, then it should just have the definition of the Hamiltonian, or the perturbed Hamiltonian. There's. Alright, so the total Hamiltonian is the unperturbed Hamiltonian plus the perturbation, right? So why do they take the difference here? Negative delta phi equals E. Negative delta phi equals E. That's where they get the negative from. But the electric field, delta phi. How do they get delta in there? Let's think. Delta phi equals negative delta phi. That sounds familiar. Negative delta phi equals E. Why does that sound so? Is that like an electrodynamics? No, not delta phone. Delta phi epsilon. No, I don't care about the sorority. Please just give me the physics equation. Potential gradient. Isn't that different though? There's F equals delta. Oh no, I guess. Oh right, in EM there was something like that, wasn't there? Okay, yeah. So negative E equals delta V. Why is it phi though? Whatever. But that's V is in the potential, right? So isn't that inverted then? equals del phi. Let's see. So E equals negative del V. And it's not like they take the derivative of it though here. So I don't know why you take the derivative either. Yeah, you don't generate a new. I guess V is a spatial derivative. So if anything, it should go to 0 if you actually took it. Unless they're integrating. They're integrating. Oh, that's okay. That's what they're doing there. But why? To get the potential? But I thought they just gave us the potential. They say the harmonic oscillator potential is 1/2 m omega squared x squared, or omega naught squared. Okay. Also the electric field. Right, so we only have the electric field. Oh, okay, so that's all to generate the potential. Okay. Okay. Shows how much I learned in electrostatics and electrodynamics, but you know, yeah. Okay, so let's see. To get the potential, let's see. We have negative E equals del V, which is just E equals negative del V. Which is equal to negative. Wait, but then how do you take the integral of energy then? The fuck is that? Or wait, no, that's not energy. That's electric field. What am I saying? Okay, yeah. So you put the electric field in, you get this weird symbol 0 cosine omega t equal, I guess, negative that equals. Yeah, let's get rid of this line. Okay. Equals del V. The potential integral with respect to space because it's a one-dimensional thing. Yet the potential is equal to then just negative whatever this is, 0 cosine omega t times x. That's where you get your magic x with no direction to it. Yeah. Okay. There we go. So now we have the potential. Now we just shove. Okay, so I guess then this is h prime. So then we would shove that into the. Or not the potential, sorry. We get the potential, which in our case, or the potential contributed by the electric field, which in our case must be the perturbation, which you would then shove into h equals h naught plus h prime. Since this already is a negative, that just means you end up with 1/2 m omega squared x hat squared plus p hat squared over 2m minus weird symbol evaluated at 0 cosine omega t x. I guess. X epsilon weird squiggly. H prime of t. Is it 1 or t? Fuck what is. At time t. At time t, that must be what they're doing. H prime cosine omega t. Why is h prime of t then h prime cosine omega t? Let me think. Cosine omega t. Cosine omega t. So h prime at 0. Oh, so we're not defining the perturbation like that, I guess. I guess we're defining it as... X epsilon. Wakaran. See another explanation. Okay. This, the harmonic perturbation. So I guess this isn't perturbation, this is just the complete Hamiltonian, I guess. Oh, you know what? I know what I was forgetting. When we talked about the harmonic oscillator in the beginning, we talked about not having not dealing with potential, but I guess it did have a potential term in it, so I guess that's just what that is. So then, going from there, how do you justify that the potential, or part of the potential is the perturbation? Xe, that weird symbol, cosine omega t, state 0, ground state, so... Yeah, I don't know. There's no point in me struggling with this any further. I'll just wait for the solutions to come up. I guess I didn't need to disconnect that because I'm not showing it on screen anyway. What is this, homework 7? Homework 7, okay. And I think I mentioned this earlier, but something is really weird with my throat recently. Like, I hope I didn't get sick with, like, COVID or something, but, you know, again, I don't know how long it'll take to actually, yeah, it's just my, then again, I guess my throat's been sore for, like, more than 2 weeks, so I guess I can be pretty confident it's not COVID, but, you know, like, no matter how small the probability, you know, I'm always a little bit concerned. Okay. Or wait, I don't know. Am I allowed to talk about COVID on Twitch? Will that get me banned? I don't know. I mean, I guess it's too late. I talk about it basically every day. Well, maybe not every day, but I reference it basically every day, so. If they banned me, I guess they would have banned me a long time ago. Okay. And I don't know. Yeah. All right, there we go. We're submitted. Yeah. 50? Oh, yeah. Wait, 50? Yeah, 50. Yeah. Okay. I gotta... Did that grade go up? I thought I got lower than a 50 in this class. Whatever. Whatever. If it did go up, then whoop-de-doo, it went up. If it didn't, well, you know, I'm always imagining things. Okay. Right, so we're gonna get as much as Operation, or as much of Operation Miyagi done as possible. And then we're gonna also cram for physics as usual. Okay, so what is this? I got a whisper. Traveler's Hook video. Let me look. Let's see. DEFCON Travelers Hook. Yeah, sorry. Well, I can't find the video right now. I'll get back to him later. Yeah. I mean, if he Googled it, I'm sure he could find it. Actually, let me just tell him that. Yeah, I'm sure you can find it. Okay, okay. Okay, so now we're in, well, we've submitted assignments. It's not really appropriate to say I finished them. But we submitted assignments. We are 100% a go. Question I'm gonna wonder about is, let me check one thing first. Let's go to my email real quick. Violent crime reported at intersection of beep and beep. A robbery occurred at the street. Armed robbery. Wow, scary. Yeah. I think there was some mention of, let's see, sent emails. Yeah, okay, so I haven't got a response back about the project, but I guess it's okay. Okay, refocus. Okay, so now I do need to have my thing connected, but, oh yeah, this is the alarm, or what is this? Wake up, dum-dum? What is this? Gura video? Beep, 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 beep. Oh shit. Awesome, he provides the... There's a Yago version? Wait, what? Oh jeez. Okay, wait, let me see what is the Yago version? Oh shit. The ground pound at the end. Oh, Yago version as in Yago's inside, okay. Oh jeez, that's perfect. Yeah. Okay. Oh yeah, I should change the title. It's Operation Yago. Operation Meet Yago mode. Okay, so I think I mentioned this before, but I realized I was kind of subconsciously copying, you know, Natsuhiro Matsuri like way more than I was comfortable with. Like it's like the hair color choice was like gradually like I was like, oh, this actually looks better. I'm like more like this, more like this, and then it ended up basically being the same color as Matsuri's hair. So I was like, okay, crap, let's do that again. So let's see. Well, let me close other tabs first, and I think I mentioned this before, but I finally reached the point where Clip Studio will crash. So at a 4096 by 4096 canvas in on a base model 6th gen iPad, it takes, I guess I'm at I think like probably 40 maybe. What is it? I must be at least 40 or 50 layer masks. About 30 clipping masks, and then I think another like 10 regular layers. And that's about the point where it starts to stutter and crash without being able to recover data. So if anyone wanted to know that information, then at that resolution, at that layer complexity, that's when it starts to crap out. All right, so I'm gonna move over here, gonna enable this guy, and hopefully it connects. Out of memory. Yeah. I mean, let me just give credit where credit is due. It survived that many layers. Like, so what I ended up doing was I basically did all these effects for this hair so far and just kind of take a look at it, and I'm thinking I'm just gonna have to be satisfied with this because I don't think I have the time to make the hair look any better. Well, I'm gonna add a little bit more of highlights, but basically this is kind of the preview before I kind of finalize everything. And yeah, it's literally out of memory, I think. But I have to give credit where credit is due because it's a 4096 by 4096 canvas, and it's about 100 layers in total with various, effects and stuff going on. So I have to give credit where credit is due. I'm surprised the iPad even survived this long, especially considering that Procreate will limit you to like 8 layers at this size. Like Procreate's like, oh, you can only do 8 layers, or not 8 layers. I think it's more like 20 layers. But Procreate's like, oh, you can only do 20 layers. But Clip Studio Paint's like, oh, I can handle 100. So I got to give credit where credit is due. But yeah, so this is I think basically the final kind of look that I'm going with. I guess there's a couple of things left to decide. The hair color, which oh, I can't show you guys now actually. I guess I can. Let me disconnect the screen real quick. Again, I don't know if anyone's really watching, but kind of so I can kind of speak my. It's basically vlogging at this point, which is why I think having the vlog tag is appropriate. Oh, I should close the previous canvas before I open the next one, or else that's really going to crash it. But yeah, just to say that the hair color that I was kind of subconsciously using was, or that the hair color that I was using was like I was subconsciously making it really close to Matsuri's hairstyle. So I just kind of full on, I just like made it, gray, and I was like, okay, if it's gray, then it's not copying her at all. I mean, okay, right. Well, it's not intentionally copying the color anymore because there is no color. Where is? I guess if I disable these two, yeah. Is that what I did? I guess I did it like that. So it's not gonna look good because the layer masks aren't applied properly. Will this connect? Hopefully that'll connect. Please connect. Okay, I think it connected. Yeah. So the layer mask isn't applied properly, so you can see all this like where I kind of went past the lines. But once you take this layer mask and then apply it to every subsection that I have, established down in the finalized layer kind of layout, it doesn't leak onto other parts. But like you look at this color, and while I did make it lean a little bit towards gray, like the base color here I modified to gray, you can see how like subconsciously I was basically using Matsuri's kind of like reddish light brown with like a bit of desaturation like color there. So that's why this is a, oh, that's not what I meant to click. That's why this is a no-go. Yeah, don't save. That's why, oh, let me close the screen again. Yeah. So I think this is it then, really. Oh, see, it crashed. Sorry, just now as I was opening the file, it crashed. Yeah, so I think I've reached the point where I can't really do anything. So I guess what I'll have to do is, man, I should have bought a drawing tablet because I don't have any way to control my. Oh wait, no, I have that monitor. Let's see. Can I do that though? Let's see. I might. Okay. fuss with that today then. Okay, first I need to check if sorry, I'm gonna be right back. I need to check if I have the drawing, the pen for my drawing tablet. I don't know if I brought that with me, but if I did, then I think I'm just gonna tear the monitor. This is gonna sound stupid, but I'm using the drawing the drawing tablet like monitor, like the drawing monitor that I have as the monitor for my hypervisor because it's so finicky to deal with. But I'm gonna pull that off, connect it to the VM, and use that to draw. And then I'll just download Clip Studio Paint on my computer. So first step for that is go find my drawing tablet pen. Yeah. First try. I knew exactly where it was. I did lose the clicker on this guy though, so I can't actually use any of this buttons on it. But it's okay. I just need position and pressure information. Oh, that would have been bad if I lost that. The nib just fell out. So I think, let's see. So if this is dead, I'm gonna have to go get batteries tomorrow, which is okay. We'll just make a trip. I have to make a trip to the where the fuck is it? I have to make a trip to the well, I was gonna say the convenience store at the corner, but I think I might go to Target because I have a hard time believing they have batteries at that convenience store. Okay, we don't have time to fuss with this shit. Oh, and I don't know if anyone's watching. Who's watching right now? I don't know. Well, actually, I guess the question is anyone here that's watching, have you watched Jakukyara Tomozaki-kun for this week? Because I gotta talk about that show. If no one, if you're not watching, or if anyone's listening really, but if you're not watching Jakukyara Tomozaki-kun, like, I think it's a really good show. Is it as good as, say, like Ore ga iru? No, not really. I'm gonna be honest. Like, let's not get carried away. But it is a good show, and it's not in the same vein, but it's in a similar vein. It isn't. It's got that same, like, it's got a similar clash of ideals and, like, trying to, and like personal development in that sense. I am thoroughly impressed by that show. Alright, so let's see. What I gotta do. First, we are killing the VM. And actually, we're gonna kill the main PC too. See, it's so good that I have a separate PC for streaming. It means I can turn off a computer without worrying about the stream. Of course, the trade-off being that the stream PC randomly blue screens, but we're gonna do what we can. We want to fully turn this guy off. Gonna go steal the monitor from the hypervisor. And yes, I'm using a Type 2 hypervisor. Sue me. Well, please don't sue me, but, figuratively sue me for what it's worth. Where's the power supply for that? Where the hell did it? Okay, here's the monitor. Oh, no, I do have a DVI port. See? It's all calculated. I have an extra DVI port left. Okay, so we'll pop that out. I guess I didn't have to turn off the computer. I could have just, like, pulling out a monitor isn't gonna kill the damn thing. It'll complain, but, won't die. Alright, so that's that. We got the display output too many drives here for. Why do I have this many drives? Oh yeah, because I have a shit ton of VMs on this for VM images, of course. Anyway, oh yeah. So yeah. Anyway, let's focus one thing at a time. Can't finish or even remotely come close to finishing Operation Meet Yago if I focus on my attention on too many things at once. So display output. Okay. Here we go. Okay, so where's the power supply? Here we go. Alright, now. Okay. So it's this one. So that shouldn't kill anything. Yeah, okay, that doesn't kill anything. Okay. Alright, so we need to establish workflows. So what are the workflows that I need? I guess I need templates. I need video editing template. Oh, I didn't want to drop those scissors. Alright, so while I'm thinking about this, templates. I need templates for. Okay, so I need to set up some archetypes for what kind of content I'm gonna make. And then I need to set up video templates for each one. Oh, did I just hit? Like, I really need to clean my room at some point. Like now. But I'm not. We'll do that tomorrow when I feel like it. So never. Okay. Alright, there we go. That's a thing. Oh, it's calm foot now. Yeah. Long-term goal, switch all my monitors except for my primary one to portable monitors. Oh, we don't. It's not this much of a hassle to switch anything. Where do I mount this on? Oh. It's garbage. I need to take out everything. I need to take out all this stuff at some point. Especially since I'm going to be doing some soldering on stream the upcoming week. I need to make my desk look a little more presentable. Yeah, right. Alright, so we'll mount it against. Let's do this corner. I was thinking about not mounting stuff to the corner of my desk, but I'm like, I don't even sit on that side of the desk anyway, it's fine. Make sure not to scissor my hand and monitor out. That would be painful, and that would also be deja vu. Oh, I wonder if I can mount this on the other side. Okay. Let's see. Oh, that's not gonna work. Who am I kidding? きつ。Oh no, that's not the right way. All right, there. I think that's. Yeah, I don't think that's. Is that good? Yeah, that's not going anywhere. All right, so let's move this monitor like this then. Like this. どの道邪魔になるな。どの道。こうか。All right, yeah, there we go. It's off the desk, so that won't get in the way. Okay. Well, the keyboard or this will get in the way, but whatever. Okay. So we'll hook up the power over. No, we'll hook it up on here because I don't know if that outlet's going to be able to take anymore. Okay. Next, we got our display cable. Oh, come on, please. Please. Okay. We got this connected. We got the Oh, I don't want to connect the USB yet because forgot this guy's actually kind of finicky about when you plug in the actual device. So we're gonna use our little portable 2.5-inch monitor as our hypervisor monitor now. Good thing it's so convenient to have 5-inch monitors. Everyone else should try it too. You never know when you'll just need like a random 5-inch monitor. Where am I gonna put it though? Oh, I got an idea. I got an idea. Let's see. Plug that in there. So we just need another USB. Yeah, there's space over there. Where is it? I'll clean tomorrow. Today's just about making sure things work. Alright, so we got that power. Oh, I should start charging my LiPo batteries. This will be funny. Ow. There. And then we'll use some push pins. Oh man, if someone saw this, they'd be like, what the fuck? So we're gonna dump this into here, along with the power cable. There we go. Oh man, this is hilarious. I'm gonna definitely take a picture of this and throw it up on the Discord later. Okay, how do I tie these together now? Tape. Why not tape? It's tape, you know. Two push pins and this guy. Sorry. Oh no, shoot, it doesn't work. Okay. I'll have to use more push pins then. Okay. Okay. Yeah, okay. Maybe I should throw it on Twitter instead. Okay, please work. Please work. There we go. Will it show display? It should, because that's an adaptive, or that's an active HDMI to or DisplayPort to HDMI. Okay, we're getting green light. Okay, please turn on. Oh, we got an image. Okay, please work. It's too small. I can't see any of the text. If it'll just boot into the login. Oh, we got a Ubuntu logo. It's hard to see the color. Oh, why the hell is the default state portrait? Okay. Okay. What is it? Is it even on? Turn off the lamp. Oh, okay, we're in. Okay. Display. Displays. Okay. Orientation. Oh wait, this is landscape. What? What is this then? Fuck, I can't read anything. Oh, did something happen? Rattling fans? Oh, sorry. I think... What is that? I don't think I bumped into anything. LZT 7-inch. That's what it shows up as. Resolution. So adjusting orientation somehow doesn't do shit. Thinks it's in landscape. Rattling fans. I wonder what it is. I don't think it rattles any more than usual. Anyway, Let's see. That's impossible to see. So I know that there's some adjustment buttons on here somewhere. Okay, no, that didn't do shit. Okay, that's brightness. And I think that's okay, so I only have brightness and okay, yeah, no, I can't tolerate this. I can't tolerate bending my neck sideways the entire time. Sorry, I'm trying to figure out what the heck. Sorry, I see the okay, you know what? Do you guys have access to my Twitter? I'll tweet this. What the heck I'm trying to do. Here. Show you what I'm struggling with. And it's not like a technical struggle, it's just you're about to go to bed. Okay, never mind then. Yeah, so basically I have you know that small 5-inch, I guess it shows up as a 7-inch, but the 5-inch HDMI monitor I have. I have that push pinned to the wall and hooked up to my computer, but I'm trying to turn it so that but the display is off by like 90 degrees. So I'm about to go to bed. I just want you to see that. Okay, shoot. I'll get to it as soon as I turn the computer back on. Sorry, let me get the display in the right orientation so I can actually get to the VM manager. Let's see. I'll try restarting it. Maybe it'll go into portrait right next time. Please. Please. I guess I could push pin it at another 90 degrees, or I could push pin it again, but why is the default state portrait? What idiot said that was a good idea? Okay, I think I just need to hang this up portrait. Okay, there we go. Okay. So I'll hook it up like this. There we go. This better work. I'll turn this down a little bit more. Okay. Please hold. Please hold. And, oh, you know what? We can hold it down like this. Okay. That'll do. That'll do just fine. All right. So, step 1, get an alternate display for the hypervisor. Looks to be good. It's a little bit janky, but I mean, since when haven't the things I've done been janky? Yeah, it doesn't look like the display's under any weird tension. It's just the ribbon cable doesn't look like it's being pinched by anything. I think we're good. Yeah, just have to tolerate the hypervisor being on a portrait display. I guess it'd be fine if it was just closer to my face, but right now it's like a meter away from me. So imagine a 5-inch 2K monitor placed vertically a meter away from you and trying to read the text on it. Okay, yeah, it's fine. It's fine. I mean, I already know where I could pretty much navigate this blindfolded, so it's okay. Come on, just play. Yeah. All right, so step 1, we've got a display for the hypervisor. Okay. You know, actually, I like that. I think I'm gonna buy another mini monitor like this, and I think I'm gonna just embed it into the computer, because I've always struggled with carrying around the display for the hypervisor. It's always extra weight. But I think that's what I'll just do from now on. I'll just use these vertical ones, which means I need to buy another one. Ugh, more money. Okay. Okay, we got display. Yes. Okay. Step 2. I need to go to Yanova's. Yanova. I believe this is an MSP19U, not the 19U Plus. Drivers. Is it Panda City or Yanova Tech? I don't remember. But you know what? Here, let's show it on. Alright, I guess we don't need to. MVP Net 16 U Series driver. Series tablet driver V 5.819U Apple Mac Windows 10 U Series tablet driver. Okay, so it's either this one, the 10.04 driver, or do they have a newer one here? Actually, scratch that one. Okay, wait. If you're gonna link me something, give me one more moment. I'm gonna pull open the stream manager right now. Man, what is the display order? Connecting to chat. Sorry, it's still connecting. Okay, while I'm still connecting, let me reorder these displays. What even is it right now? Oh, that's okay. So let's. Number 4 is on the far left. 1 is on the far right. 2, 3 are in the middle. There we go. Okay. Yeah, feel free to link it now. I'm connected to chat. Finally. 10.04 does appear to be the most recent version. So let's just download it straight from the manufacturer. Wait, no, that's a 19U Plus driver. So then let's just download 10.04 from the manufacturer themselves. For driver installation, download and unzip to your local drive first, then install from local drive to avoid the security warning. Huh? Well, that's sketch. That is sketchy. What? They give you an executable. That is sketchy. Sorry. Downloads, and there's a folder. Where is it? Okay. I mean, as sketchy as it is, the executable just does appear to just... That is sketchy. That is sketchy. I mean, I guess everything I have important is already secured with two-factor authentication, so even if they, like, installed a keylog or something. System has detected that tablet driver has been installed. Oh, really? Do you already have the drivers on this? Yeah, Yanova, not cool to be installing, or not cool to be having users run an executable. I mean, I guess Windows Defender and shit didn't trigger anything. I'm gonna run Malwarebytes on my computer once after this, just to be sure. Unless there's another free, utility that everyone knows of that would be good to run as well. Okay, tablet monitor is ready to go. Okay, let's see. Okay, so here's the video. The Botan wakes up. Oh, wait. This meme, okay. Oh. Oh, perfect. Sorry, the Botan one was good, yeah. Sorry, I'll take a look at the other one first. Let me just make sure my monitor works. Okay, so we got, it appears to be relatively calibrated. Yeah, unfortunately it's on the other side, so I have to kind of talk and then flip over and talk and flip over. All right, let's get Clip Studio Paint. Clip Studio Paint. If I'm that would be the energy, yeah, it would, yeah. Okay, so free trial on Windows. Great thing is we don't have to worry about shit because we can just reset the VM, Don't need to deal with any registry BS. If they go by IP address, then we'll just run a VM, or not a VM, we'll just run a VPN, etc., etc. Yeah. The problem about this monitor is that it's just so slow to update. It's like you can see yourself doing, you can see yourself drawing on it, but the screen isn't remotely the screen refresh rate isn't remotely, fast enough to make it seem natural. So, okay, so we're installing Clip Studio Paint right now. I know you guys can't see it, but oh, I wonder if I can't really mirror that, can I? If I mirror it to let me think. I'm gonna try it actually right now. Well, let me install first. But what I'm gonna try is, I know my capture card only supports 720p and 1080p, which sounds really stupid, but it was a cheap $30, PCIe capture card. All right, yeah, it sounds good. Yeah, yeah. Thanks for staying till the end. Take care. Stay safe. Have a good evening. We'll see you later. Yeah, sorry. So yeah, the capture card's is a cheap one, as I mentioned before. So it only supports standard definition, high definition, and full HD, I think. Actually, it supports 1080i awkwardly. So my monitor, which is I believe 1440 by 900, I think. It's one of those awkward resolutions. I don't know if it'll show on screen if I try to mirror it. Sorry, let me see. So duplicate, extend, keep changes. There we go. And I believe monitor, let's identify 1, 3, 4. Okay, monitor 2. So I want to mirror monitor 2 and 4 to each other. Okay, keep changes. What? Oh, okay, so that should have worked. So what kind of disaster do we get over here? What? Oh, wait, can you? Oh, okay, now the thing is messed up. Okay. Let me just let's see. Tablet, where's my tablet? Shit. What monitor is everything connected to now? Okay, so if I go to the left, I should, okay, yeah, okay. So this is on the far left, so we'll apply that. I think is okay to flash that on screen briefly, even though that wasn't intentional. Okay. So first step, we need to pull up the calibration software. And where did my mouse go? Oh my, did it change the locations? Like, oh no, it's like this. Okay. Yes, it's like this. Apply. Yeah, okay, here we go. So calibration, oh, it's monitor setting. We want it on monitor 2, apply. So now if I do shit, you should be able to see my cursor on screen. If someone could do a yes or a no or something in chat, that would help. But I mean, even if you don't, I can see it happening, so it's okay. 4-point calibration. Oh, cancel. Let's try that again. Click. 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 And click. Obviously, we're not expecting much from the calibration, but if it's relatively close to my cursor, then I'll be happy. Okay. So now we want to do Clip Studio. Clip Studio. Wow, it's in capital letters. All right. Will Clip Studio run properly on a such a small screen? I don't know. Paint. Software started. Please wait. Okay, connecting to server. Already have a license. Sign up for plan. Using a trial. Let's keep using the trial. Please let me in. Please. Thank you. Yes. Okay. Okay. Ta-da. Oh, that's small. There we go. Okay. There we go. Okay. I can't do this. I need to move the microphone. Let me disconnect it real quick. Yeah, sorry. I don't know where to connect the microphone. Give me another sec. Okay, I think this is good. I think this is far enough that I won't collide with it, but also close enough that I can actually talk. So first of all, let's try to get a grasp of things. I need another keyboard. Let's see. Well, okay, you know what? No, I don't. I mean, you know, we struggled so much on iPad. I'm sure we can figure something out here. So let's kind of boost the canvas. Let's see what it feels like to run this. Look, it's so small you can't see any of the pencil options. Let's just do like, let me keep it on real pencil. Let's see how it works. Oh, pressure sensitivity is working. Yeah, pressure sensitivity is working. I suppose the real question is here. What we want to know is, like, for example, how well will it work if I say, what should I try? Let's like, for example, on my actual drawing, I would have taken, for example, a G pen and let's just make it black. We just had some black area here, for example, like the sphere. We're like practicing the what do you call it? The shading. So we had, oh wait, no, that's not what I want to do. Where's undo? Here it is. See, it's so okay. Okay, you know what? Clip Studio Paint seems worth it. I know I sound really stupid, but it really seems worth it. Because with the full version, I believe you get access to all devices, right? Or there should be an all upfront cost. And it literally just feels like the same as the mobile, or I guess it's probably proper to say that the mobile version feels the same as the desktop version. That's absolutely insane. Oh, and I guess my facial tracking is busted, but it's probably because I'm so far to the thing. You know, you'll just have to forgive that the facial tracking's busted. I mean, it can't see me anyway. Right, that's crazy. Okay, so back to reality here. Like, for example, okay, there is one thing that's different. Long press doesn't let you do that. What was I trying to do? Is layer mask max size. Okay, that's what it is. Okay, so we would then dump the color black on here, but then color using the G pen, for example. And then you get this, for example. And if I wanted to practice shading, for example, and maybe make the side gray or something, then I'd do this. I'd grab the airbrush tool, and let's try softly brushing gray. That's not soft at all. Undo. What's the size of the tool? Or, you know what? No, that, oh wow, that's, yeah, okay. That's good. The sensitivity is a little bit different, so I'm gonna have to modify the curves for it, but okay. Yeah, so this will work. It feels a lot different from the Apple Pencil, no shit. It's like 4 times older, but okay, we can work with this. Okay, we can work with this. Yeah, so it's funny, right? Why the fuck did I paint for the mobile version after the desktop version? But it's okay. You can use limited feature. I thought the trial gives you unlimited. Okay, whatever. So we know the plan now. We're gonna finish this on my computer then, or are we? Wait, how many? Sorry. Device man, or actually, what is it? What am I looking for? Do I have? Well, task manager. Does this computer have all the cores dedicated to it? Sorry, let me see. 2, 4. Okay, so I have 10. So 2 or 5 by 2. Although It's not showing the core and thread allocation. Base speed 3.75, yeah, 12 without use 4 for the hypervisor, sounds about right. I have the 760 attached. Okay, yeah, so this is as good as my computer's gonna get. So let's export my current drawing. Let's see, what does that mean? Okay, so that means I'll have to take not the final reduc, but the final with all the yeah, we're just gonna start now. We're gonna grab a coffee. We don't have time to be like, oh, let's take a nap, you know. No, we don't have time for that shit. Okay. And why am I not allowed to attach? Okay, you know what? I guess I gotta export like that. Okay, files. Okay. On my iPad. Key update final. Not the reduc. Green test. Oh, I guess it is the reduc then. Yeah, okay. Okay. So we want to export this share to Gmail. The files you're trying to share exceed the attachment limit. Okay, discard. What else what can I share it on? Oh, I bet I have Google Drive on here, don't I? No, I don't. What do you mean I don't have Google Drive? No, I have Google Drive right here. Oh, it got uninstalled. Oops. Okay. Okay, come on. Let's go. Where's this? Okay. Okay, well then let's get a better grasp of the density, or the, not this is the one I want to do, a new layer, please, thank you. The pressure sensitivity. Okay. Yeah, okay. How does the pencil look? How does the G pen look? Am I letting go too early? Okay, I think I can control the weirdness there. Okay. Alright, so Google Drive is back. Let's see if I can share it now. Share Google Drive. Here we go. Thank you. I guess my personal account. Upload. Alright. Okay, it's working. Okay, come on. I think I will actually take a break soon. As soon as I know this works, that will give me the reassurance that I can go to sleep and get started tomorrow morning. So, so he said, but realistically, what's going to happen? I'm going to stay up until midnight like last time, or 4 o'clock like last time. What an idiot. Let's see. But yeah, okay. We might need to move our workspace a little bit to, I guess, yeah, let's do that. I need more monitors. I need a monitor and a monitor and a monitor and a monitor. Okay, upload, please. I just need to make sure I can open the file. There could be like a, oh, you know, you're not allowed to open this file on, you know, these kind of, you know, licensed accounts, in which case I'd need to get another license. But again, I think Clip Studio is worth it. I might actually let me look it up real quick. How much does a full license of Clip Studio work? or pay, come on, Clip Studio Paint. And we'll do Pro because I know that there's a bunch of good features. I can't afford the Pro version. One-time purchase. Clip Studio Paint Pro, $50. Huh? Oh shit! Wait, no. Let me get my freaking wallet then. Oh wait, what does this give you? What does this give you? Does this give you unlimited licenses on all devices? Because if it does, that's like a fuck yeah, it's just $50. Did this get cheaper? I think this got cheaper. There's no way I wouldn't have paid for it if it was $50 before. Okay, anyway. Google Drive. Cloud storage. Go to Drive. Crap, I shouldn't have put so much pepper. Download. Anyway, no, it's not a virus. I freaking uploaded it myself. Now, how big is this freaking file? Okay, 133 megabytes or something. Okay, cool. Let's... crap, I can't. I'm gonna have to move this off screen. File, open. Downloads. Open. Please just work. Please don't crash. Oh, come on, don't crash. It's only like 100 like layers. Like, please don't crash. Oh, Clip Studio, you can do it. You better not be running on one. You better not be running on single thread. Let me make sure. This application better be multi-threaded. Oh, don't give me that. Wait, what is the 32-bit part? That better not be the main application. I don't care if the launcher is 32-bit. The main application better not be like a 32-bit application. Oh, wow, that spiked the memory usage. Oh, wow. I'm hitting... It's using 7 gigabytes. Wow. It's using that much. Close Google Chrome and stuff. I mean, we need one tab open, but we can close everything else. That went down by like 0.1. Yeah, wow. Clip Studio Paint's using... Okay, I think that's a good excuse. I need more RAM. Crap. I don't have that money. Oh, it crashed. So I think the takeaway is that just download more RAM. Yeah, just get some Optane, man. Did you hear that they're stopping development on Optane? I'm a little bit disappointed, to be honest. I thought... Oh, is this caching properly? Oh, holy crap. I think we hit another roadblock. I think the complexity on this file might be a little bit too much for the thing to handle. Okay, so if that's the case, I have to ask, how optimized is the iPad version then? Because the iPad version finally started crashing at this level. Are you telling me that the iPad's running has equivalent optimization as a VM with... Is this hardware accelerated? Let me double check. File. Preferences. Performance. Free space. Location. How do I only have 20 gigs of free space? Even then, you know, caching related issues, but still. And wait, this is running on an SSD, so there's no way that should be a problem. Oh yeah, there's only 20 gigs of free space actually. Oops, sorry. Available memory size to use. This change takes effect. 10 gigs. Don't I have 12 allocated to this? I don't know. Why is Does this do GPU acceleration? Let me check. Does Clip Studio Paint do GPU acceleration? Oh, come on. Someone's like, oh, it's Clip Studio Paint's totally single core. But wait, no, I see my load balanced across all cores. Yeah. So it does seem like a RAM bottleneck. I mean, you know, looking at my task manager, you can probably see that, right? Like, what is this? What is this? But no, it's not single core. I'm pretty sure it's not single core because you can see it does appear to be load balancing. Well, this core actually looks like it's taking a lot of hits, so maybe it is single core. We'll watch it while we're working on it. All right, so allocate to application. We'll just make that like 85. I mean, if an iPad can handle 85, then I'm sure my computer can handle 85. But is there really no scratch disk? Or wait, what is this allocate to application even? Is this the free space as scratch, or is this memory? That looks like memory because it just went up. Okay. Is there really no other privacy settings? 3D, quick convert file, canvas tool, tablet, tablet PC. Application, input frequency, prefer speed. We'll try prefer speed first. Tools with finger, I don't have anything like that. Okay, so we'll see. 15, it was 15% isn't, nope, it's still lagging. Okay. Oh, that's not too bad though. No, okay. So, wow, this is, I don't have space for anything on here, really. Yeah. Okay. But okay, so there's a couple things I do want to try, I guess, then. So, I guess, like, let's say hypothetically I was like, oh, let's add a new layer. Let's call it test layer. All right, and we're going to make it a clipping mask. Oh, it already is one. Is it applied already? Yeah, I guess it's already applied. So let's try, like, let's go to test layer. Let's add some magic green. Like, I don't know. Let's do some shit on here. I don't know. Okay. Okay, so let's, like, is this what this is rotate. Oh, see, that's convenient. Okay. All right, go to 0, please. Go to 0. Thank you. Zoom? Okay, that's zoom. Okay, awesome. So you do have, like, on-screen controls to help. Let's say I wanted to do, like, let's say I wanted to do the harsh highlight. So actually, we're gonna want a green, or sorry, yellow. Like, we're gonna want, like, a orangey yellowish thing way out here in the white area. Right, I want something like that. Let's zoom out a little bit. Shigeru suggests dense watercolor. Yakimayuru suggests watercolor tools in general. I believe Inuyama Tamaki also uses watercolor. We're gonna just copy them. Oh, this isn't the top layer. There we go. That's not big enough. Get all the brush size, Why isn't this on the... It moved the layer down again, didn't it? Okay, there we go. And then we switch to transparent and then lower the size a little bit and start shaving away at it a little bit, I guess. Definitely not as easy to use as the iPad, unfortunately. I mean, no shit, it's a tablet with a dedicated stylus versus, Windows PC with a cheap drawing monitor tablet. A cheap Cintiq clone that I think I mentioned before. I got it for $80 on Craigslist, I think 5 years ago. Maybe a little bit longer. Maybe a little bit less than that, I can't remember. It's not supposed to work the best, but it'll get the job done. I think I mentioned before, why the hell would anyone be getting rid of any drawing tablet for $80? Well, it's got a really sketchy power adapter, so actually no, wait, but we disassembled this power adapter on stream one time. There was nothing wrong with the power adapter. It was just covered in like electrical tape for whatever reason. So I still don't know what the issue with this thing is. Oh man, that feels so good. Although I do notice I have this scratch on the screen right here, which is why there's clicking sounds. Move it away from the scratch. Oh, now I remember, the scratch is one of the other reasons why it's cheaper, because you just have to avoid that scratch while you're drawing. Okay, so and I think the person said that their mom was buying them like a Surface Pro or something. Freaking bougie kids. Yeah, again, I could I'm not actually mad, because it's thanks to those bougie kids that their that their old hardware rolls down to me. I'm not going to complain about some free hardware. Yeah. One man's trash is another man's treasure, right? Or one girl's trash is another man's Cintiq. Yeah, it just depends on how much tolerance you have. So I'm gonna end the stream soon. Okay, so you can see I'm not really doing the shadow all that well right now, but again, I'm just trying to get a feel for the drawing tablet. Ironically, it feels like it's a little bit, and I think this is actually not because it's better, this is more accurate than the Apple Pencil. I think it's because my Apple Pencil's broken. I fall asleep in class, so I've dropped it at least, if I said a couple hundred dozen times, then I think that would still be an understatement. I think I need to check there's like, oh, whoops, that's too close. I think I need to check the mechanism on it, because I think it's busted. And you can get a used first gen Apple Pencil, which is what my iPad is compatible with. You can get those for like $60. In fact, I bought mine initially for $60 at a pawn shop. So it's so funny. My mom was like, my mom went with me for whatever reason, but the pawn shop was like, it was one of those, I wouldn't say it was a sketchy pawn shop, but it was in kind of a questionable area. So she like she was waiting outside while I went in, because I had called, they had advertised on Craigslist, so I just called ahead and was like, yeah, I want to take a look at it, would that be okay? And they were like, yeah, they were fine. But when you go in, there were like 3 layers of, like, there's first the metal fence door at the front of the building, And when you open that, you get buzzered in, and it opens the second set of doors, which is like the regular doors of the uh, of the pawn shop. And then when you pass those doors, there's a third set of like fence doors again. That just opened normally, but it was like, and you saw like guns on the wall. I mean, obviously it's a pawn shop, of course they have guns and shit. Well, I imagine they were probably airsoft because um well, I'm pretty sure they were airsoft because they had the orange tag thing on it. Of course, I believe I saw in the news the other day that there are some people that are, I can't quite remember in what district or what region, but there was some news about how people are kind of hiding real guns by making them look like airsoft guns. I can't remember why, so again, take that news with a grain of salt. Um, you know, but I'm pretty sure they were fake guns, or I'm pretty sure most of them were airsoft. I don't know if they all had the orange tag on it or not. But yeah. Oh, well. What did I just do? There we go. Hmm? Oh, I'm not on the transparent color, that's why. But yeah. So it was $60 back then, and that was in 2018, right? So even if the thing retains value, you still expect a new Apple Pencil to go for, $60, right? Of course, mine wasn't in the best of condition. First of all, the cap was missing, and I can't get shot if I don't go outside. Big brain. Yeah. Man, if Clip Studio Paint really is single threaded, I'm going to be disappointed because I'm looking at the utilization right now. It's really only at like, it goes, as I'm doing like this crap, it goes to like 14-16%. Yeah. Oh, it is hitting one core. Oh, come on, Clip Studio. They had so much of my respect. Um, with optimization. In fact, actually, that's impressive. So Clip Studio Paint works this well on one core. That explains why it just works so well on the iPad, because the I mean, granted, it's not a architecture isn't the same, so you can't compare single thread performance all that well between a x86 and whatever variant of ARM that Apple uses. But I guess if you consider that it's Clip Studio Paint apparently hasn't been optimized past single core usage, then it kind of makes sense that it would just work kind of well if you ported it, you know. Kind of makes me curious how well it'll run, because the new M1 processors, right, for Apple, those apparently have very good single thread performance as far as I'm aware. Granted, again, you can't compare it to one-to-one, to x86 thing. But if the optimization on a mobile, the core, like the, what is this? Is this an A10? I think it's an A10 core or A10 processor. I don't quite remember the core allocation, but I believe it was like a 2+2 big dot little layout for the iPad. Don't quote me on that. I don't know. But it would only be using one core of that, right? So if you consider that, then like I'm curious how well Clip Studio Paint will run once it's optimized for the M1 core. I can sense the electron from Clip Studio Paint. Sorry, what electron? Sorry, or is that a figure of speech? Sorry, I'm not familiar. The framework. Oh, really? Oh, electron. So can you give me like a for dummies like quick explanation for what exactly electron is? Because I believe and I'll check this later. Maybe you could check. I believe OpenBCI, the brain computer interface, that the company that manufactures the EEG kits for like brain computer interfaces and stuff, like the open source ones. I believe their GUI and the software that they use to manage the newer systems also uses Electron. I never could quite figure out what exactly Electron was supposed to be doing. So when I was building it when I was trying to build the GUI from source, I was like, well, what is this thing? What does this do? I mean, it's just a framework that's used to make desktop apps. They look nice, but also eat up all the memory. Oh man, I hope that's not the case, because drawing software is so dependent on what you can store in, on RAM in the first place. I hope they didn't use like a RAM hog of a thing. VS Code via Slack and Slack, for example. That wait, I don't get the resemblance then. Oh, as in stuff that uses Electron. Is that right? Is that what you mean? Okay. Oh, really? Okay. But that look. I see what you mean. Yeah. I didn't realize they used the same thing, but I thought it was just like a pattern in the industry, like, oh, they're all using this kind of look to the software. But okay, I didn't realize it was the literal framework was like like I didn't realize something on the back end was literally shared between them. Okay. See that? Okay, that makes a lot of sense. Okay. That makes a lot of sense. That being said, it must be very versatile then, because for as much as Slack and VS Code have some resemblances here and there in terms of how it looks, they are very distinct. Like so much that it didn't bother me. It didn't occur to me that they shared something in the back end. Um, so it must be very versatile then. I mean, I guess it is, right? But my point is, it kind of makes me think, like it's kind of further validation to that. Yeah. So obviously I'm not doing anything final for the drawing right now, although I guess I should be, just not to be wasting time. It's just my brain is dead, to be honest. I'm still just trying to get used to the feel of this guy. Yeah. Oh, whoop, too much erase. Whatever. Yeah. Although one thing I'm having trouble with is with the dense watercolor, it seems like pressure sensitivity really mainly applies to the size at the moment. I guess if I lowered the crap, if I lower the density of the paint, would that change? No, I don't know. Oh, maybe, yeah, no, that's what it did. Okay, yeah. I'm gonna bring it back up just so I don't mess the settings up too much, but yeah, okay. So obviously that's not the final highlight, but you can kind of get what I'm gonna do, right? I'm gonna do that, and then I'm gonna throw in the green highlights that I had initially planned for, I don't quite remember where on the hair, but these can just be single lines. And I mentioned before, by making the green highlights just single colors, single lines, it makes it easier to chroma key because there won't be like multiple shades to the green. So I don't have to make the chroma key so tight if I do the back as green. I could choose a different color like blue, but the problem with, I think you probably know, but the problem with blue and red, right, are that like red, for example, is just such a core color in the skin tones that if you used chroma key off of red, then chances are you're gonna hit the skin tone colors, right? And likewise with blue, there's just so much, like just the blue layer channel, so to speak, goes with, or just involved in so many like typical colors that it just, green tends to be the outlier in that regard. So I'm probably gonna just use a green thing, but so you can kind of get the idea, right? And as usual, yeah, I like what is this shading? Like what the fuck is this shading? I don't know either. It's not like this would never happen. It would be I don't even remember what layer I put those on. Oh, here it is. Okay, so it's this layer. Okay. Oh, I tried to sample the color like I did on iPad, but that didn't work. Color picker. Can I open this guy? And I think there. Okay. I'm gonna go to sleep. Okay. Yeah, I think I should go to sleep too. Sorry, just one last thing. So my point is like the only point I was gonna make was that like, you know, this should be more like I don't remember what tool this was anymore. Shit. Okay, but you know, this should be like everything down here should be the dark color or something, not this weird like, you know, paw looking thing. But anyway, yeah. So yeah, Konosuba, thanks for staying till the end. And I guess if there's anyone else lurking, thanks for staying till the end. I just looked at Task Manager. Yep, Clip Studio Paint is totally single core. That sucks ass, honestly. But anyway, yeah. Take care, stay safe, have a good evening. See you later. Yeah, otsukare, oyasumi. Alright, so I'm going to call it a day as well. Let's not save any of this work because I didn't really do anything substantial. Discard changes. Okay. Although the good thing I noticed, I guess, is that if I have the screen mirrored to a 1080p screen first, and then I force the capture card to mirror a different resolution, then it seems to just add borders and then get along just fine. So I think that's the trick. I just have to disconnect the screen mirror every time I want to, or I have to boot the system with the capture card mirrored to a 1080p screen, and then I guess what is. I don't know what it's showing. Let's just mirror. Okay, extend, duplicate 2 and 3. Okay. Keep changes. Okay, I think that's good. Yeah. All right. So so that's the end. Operation Miyago will continue for the whole week because there's less than a week left until the submission for Hololive applications. So it's gonna be a rough week, but you know we're gonna try to do it. Yeah. So see you guys later. Otsukare, oyasumi, owari.